Hello, everyone. Welcome to this ninth podcast brought to you by the Vatican Observatory Foundation. I'm your host, Bob Trembley, factotum for the Vatican Observatory Foundation, volunteer NASA JPL Solar System Ambassador, and Director of Outreach for the Warren Astronomical Society in Michigan, at least for the next couple months until I'm term limited out of that position. With us is Brother Guy Consolmagno, President of the Vatican Observatory Foundation and Director of the Vatican Observatory. Our guest for this podcast is Dr. Christian Koeberl, the Chair of Impact Research and Planetary Geology and the Deputy Head of the Department of Lithospheric Research at the University of Vienna. Impacts and cratering are topics that I find fascinating, so this should be a real treat. Welcome, Christian.
Hello.
Great to have you here.
Impact craters are the most fundamental form of geological activity in the solar system. Describe some of the ways they've shaped the planets.
Well, as you just observed, impacts basically are everywhere. And all planetary bodies in the solar system that have solid surfaces, I have to make that distinction, are really covered by impact craters. A good example is to look at the moon, and everybody who has ever taken a small telescope or binoculars and looked at the moon will have seen that the moon is covered by craters, lots of craters. Incidentally, the first person to ever notice that with a telescope, at least on record, was Galileo Galilei. And he published in his Sidereus Nuncius in 1610 very nice drawings of the surface of the moon taken through his small telescope, which he built himself. And what he noticed is that there's lots of craters, and he deduced that from the way the shadows were going. So he could find out that those are not mountains, but those are actually depressions. Now, Galileo himself at that time did not know how these craters have formed. That knowledge kind of came later, but lots of people were thinking, well, they could be volcanic because that was what people saw around them. There were volcanic eruptions, volcanic craters, especially in Italy, where Galileo was living at the time. And so that kind of quote mark knowledge went on for a long time, actually into the 20th century. And the story about how craters on the moon actually formed really changed only in the 20th century. So historically, that was very interesting. In the late 17th century, there was a British scientist, Robert Hooke, who made even some experiments on the formation of craters by throwing objects into basically a muddy surface. And he noticed that the features that came out looked like the craters on the moon. But his very interesting conclusion was, well, even though they look similar, they're probably not the way how it formed, because, and here it goes, the space between the planets as we know it is empty. And that was the knowledge in the late 17th century. There was nothing flying around in between the planets. Meteorites were still thought to be concretions that formed in the Earth's atmosphere, maybe similar to hailstones, or come from distant volcanoes or things like this. So the first minor planet, the first asteroid, was only discovered, incidentally, also in Italy, in Palermo, in 1801. So then suddenly more and more were discovered of these minor planets. So suddenly the space between the planets was not empty. And more powerful telescopes, and then later, of course, study of planets by spacecraft, showed us that more or less every planet, Mercury, Mars, the moons of the outer planets, they're all covered in impact craters. And even now we have some photographs of the surfaces of minor planets themselves taken by spacecraft, and we see there is impact craters even on the minor planets. So collisions happen all the time between larger and smaller objects all over the solar system. So it is probably the most widespread geological process affecting the surface of all planetary bodies in the solar system.
To give you a sense of how recent that all is, the guy who wrote the book, literally, on impact craters, is a fellow named Ralph Baldwin. Did you ever meet him?
I did actually meet him, yes. He was at one of the Meteorological Society meetings in Chicago, if I remember correctly.
That must have been the meeting where I saw him too.
Yes.
Yeah.
And but that book was published in the 1940s. And so it's very interesting if you think back that even when meteor crater was studied the first time by Daniel Barringer at the beginning of the 20th century, people really did not have any understanding how impact craters even formed.
One of the great questions that came out was the fact that most of the craters you see on the moon are round. And anybody who's been to the beach in the summertime and thrown stones at your little sister or whatever, notice that when they miss, they leave long trails. They don't leave round holes. And it wasn't until Barringer, or not Barringer, it was Baldwin, who had worked during the war in explosions, saw that, if you have an explosion, that's energy, and energy is a scalar, and it leaves a round hole. And only if you have a transfer of momentum, momentum is a vector, and so it's got a direction to it. If you've got an object hitting the surface at faster than the speed of sound, so that the dirt can't get out of its way, that causes it to explode, and that gives you the round crater.
Well, you see, in fact, there was somebody before Baldwin who, for the first time, published that, and that was in 1916 already, and that was Ernst Öpik. And he was from Estonia, which at that time was a small region, but he worked that out, basically the connection between the kinetic energy and the velocity. Anybody who had physics in school may remember the very simple equation: kinetic energy is 1/2 times the mass times the velocity squared. And so even if the mass is not particularly huge, it's that enormous velocity with which these objects hit the surface of the moon or the earth or whatever that makes the difference. And so a small object makes a big crater, and the main thing is the energy that is involved there. And that's why the crater is round at the end, as you say. But the interesting story was that was published. He had just finished his studies, and he published it in Russian with a French abstract in a small Russian publication, ensuring that nobody read it.
What have we learned since the beginning of the space age when it comes to cratering, and what are the biggest questions nowadays?
Well, I would say we have learned since the space age. I think the most fundamental point, and we already kind of talked about that very briefly, is that impact craters are not just limited to the Earth or the Moon. In fact, they're very difficult to find on the Earth because there's an atmosphere that screens out some of the smaller things, and also there's geological activity, but we'll come to that probably later. But we've seen that when you go to Mars, for example, and you take images from spacecraft, which are of a quality that you can't do even from the Hubble Space Telescope or so, then you see that a whole hemisphere of Mars is covered by impact craters. And you go to some of the moons of the outer planets, and you see that many of them are covered by impact craters. And you see when you go to Mercury, the first spacecraft that went there was only in the 1970s that took photographs. It was Mariner 10. And it looks almost like the moon. It is covered in impact craters. And that was something we really did not know before, how widespread impacts are. I think that tells us something also, and also the discovery of all the minor planets and the collisions in between. I think that tells us something also relevant for exoplanets. We can, I think, safely predict that impact cratering is important in other planetary systems that we know of as well, not just in our own planetary system.
Now, I've got a question that back in the days when I was learning this stuff back in the 70s, there were still great debates going on, and I never did hear the final outcome. You've been in the field since then. One of the phrases that people would argue about is whether or not surfaces were saturated with craters, which is to say, every time a new crater was formed, it wiped out an old crater, so the general net number of craters stayed constant. Is that concept still in vogue?
Yes. So there are actually some surfaces that have not been like resurfaced by, say, on Venus, for example, there's been resurfacing going on. On parts of Mercury, there are resurfacing going on. But there are parts, first of Mercury, but mainly on our moon, and also on some of the satellites of the outer planets, where it seems that we're looking at basically saturation because the moon has not been geologically active for the last 3.5 billion years. And so you just add one impact after the other. And eventually, and on the moon particularly, with no atmosphere, even the smallest objects make impact. And that is what is reshaping the surface, the soil, so to say, of the moon, which we call the regolith. So that is the product of constant bombardment. It goes down. When Apollo samples came back to the Earth, people were looking at tiny little spherules that were visible only under the microscope. And even these tiny little spherules had even smaller little impact craters on them. So if that's not saturation, I don't know what it would be.
But that means that when you do have kinds of resurfacing, you can work out the relative ages based on how dense the surface is cratered.
Well, that is one of the ways how people who use remote sensing try to get at least an approximate sense of age of a planetary surface. You look kind of what is the distribution of craters? We know from the impact flux that small impacts are much more common than large impacts. And so basically, if you have a relatively young surface, all you'll have is a few small impacts. And the older the surface gets, the more larger ones appear as well. So you can use that on the one hand to relatively date age differences between different types of surfaces, but also get an approximate idea of the age of a surface. And that is being used on Mars, on the moon, and some other objects as well.
Well, what's your research? What are you actively working on right now?
So what I do is I mainly study impact craters on Earth. And I do that by looking at geochemical aspects, petrographic aspects, and mineralogical aspects. So basically, one of the things I work on is how do we identify impact craters? How can I tell that what we're looking at is actually an impact crater and not some other kind of crater structure? Because especially on Earth, that is difficult. On the moon, it's much easier, in fact, because almost everything that is a crater is formed by impact. On Earth, we have other processes as well, such as volcanics, collapse features, karst features, wind features, and many, many others. So it's not immediately obvious that something formed by impact. And in addition, because on Earth we have an active geology going on, the surface of the Earth is constantly changed. And craters are, on the one hand, being eroded, like you have gigantic sandpaper basically eroding away the surface of the Earth. Craters disappear with time, and what is left is maybe only the deep underground. So it's not a nice little crater feature, a hole in the ground like where it used to be. And the other thing is that craters can be covered up. And so you need drilling to get to them. And so when you finally get a sample, you may only have a sample, but not a whole geological feature. Because, for example, Chicxulub, one of the larger craters that we have on Earth, that is 66 million years old and is related to the extinction of the dinosaurs and other species at the time, is not even visible on the surface of the Earth because it is covered with several hundred meters of younger sediments. So we needed to drill there. And then you have a small little drill core. And so you need to do some studies.
How do you even know to look for a thing like that if you can't see it on the surface?
Well, in that case, there were some geophysical indications that we had around structure deeper down. And so then drilling happened. First, there was some drilling because people drill everywhere for petroleum and gas. And so there was some drill cores already available. But then people were looking for where the hell is that impact crater that killed the dinosaurs. And they were looking all over the place. And then suddenly these old petroleum company data came up and said, oh, there's a round feature here. Let's try to drill new. And so there was some new drillings going on. But then what you need to do when you get these small little chips and core samples, you need to make thin sections and look at them under the petrographic microscope at high magnification. And then you see that some minerals show characteristic changes that are the result of the impact shock. And these shock features, for example, people may have heard of shock quartz, yeah? And they have these lamellar features that you see under very high resolution in the microscope. And so this is something we're looking for. So we look for shocked minerals. But also one of the things that I particularly do in my laboratory and have been doing for the last 30, 35 years or something like that, was to look for geochemical traces of the original meteorite. Now, this is not so easy because, as we have already talked about earlier, what you have is a relatively small object that makes a relatively large crater. And so the difference is that the impacting meteorite or asteroid, whatever you want to call it, makes a crater that is typically about 20 times larger than the impacting body. So the mass difference, of course, is even larger. So you have a tiny little amount of extraterrestrial material, and because of the shock that you have, it shocks a large amount of terrestrial material, and the meteorite itself is basically vaporized. It goes up in thin air. It is mixed in with a much larger amount of terrestrial material. So we're in a situation similar to, you have a big pot of water and you add a little bit of salt to make your soup. And so the meteoritic material is that little bit of salt that you add to a huge pot of water. So the task of the geochemist is to find the traces of that salt, to find the traces of the meteorite in a huge and much larger amount of terrestrial material. And we have some methods of doing that, which is by looking at some chemical elements, but also some isotopic signatures of elements that are common in meteorites, but relatively rare in terrestrial rocks.
An example of that would be maybe the iridium that they found.
Exactly. So iridium was found back then, by now over 40 years ago, in many layers that related to the end of the Cretaceous era. And that is something, the element iridium is one of the platinum group elements, together with osmium and platinum and palladium and so on, that are common in meteorites by a factor of like 100,000 or a million, even more common in meteorites than in typical surface rocks on the Earth. So even if you add only 1% or 0.1% of a meteoritic component, you will still see that in the iridium content, for example. And something similar is also another platinum group element, the element osmium, where the isotopic composition of that osmium is different between extraterrestrial material and some terrestrial material. And we can do that as well and look at if there is an anomalous isotopic composition of the element osmium. That all indicates to us that there might be an extraterrestrial component in there. And if you combine that with petrographic and mineralogical evidence, such as shocked quartz, shocked feldspar, shocked zircons, or so on, well, then we're on a good trace of a meteorite crater.
So as I remember, the first layer that had that iridium that got people excited was from Italy, not that far from Florence. Did you go there? Were you able to study any of that stuff?
Well, yes, not at the time when it was first discovered, because that was in 1980, and I was just still a student at the time finishing my PhD, which was, by the way, on tektites, which is another type of impact glass. But later on, I did go many times, and it is not far from where I now have a second home in Italy. And the location, the famous location, is the Bottaccione Gorge near the city of Gubbio in Umbria. And so I've been there countless times, and it is extremely impressive to look at that location and say, wow, here we are some thousands of kilometers away from the actual impact site. And material from that impact was thrown all over the planet. And in fact, this was just the first place where the iridium was ever confirmed. But later on, people found it all over the planet. You can find it. The impact was in Mexico, in today's Mexico, but you can find the ejecta in Italy, in Spain, in Austria, also in Sweden, or in New Zealand even, or in deep sea sediments. So you find it everywhere, all over the planet. So you can say that this impact really had global consequences.
Where are some of the other places you've traveled to in your studies?
Oh boy, I've been studying impact craters. I would say I've actually been on all 6 continents, including even Antarctica, where I was searching for meteorites, not craters themselves. But some of the more exciting places where I've been were related to drilling projects. One of them, for example, was in Ghana, in West Africa, close to the equator, where we were drilling at the so-called Buzumtwi crater. And you can imagine, so near the equator, and so we had temperatures of, during the day, 36, 37 degrees Celsius. At night, it cooled down to like 32, 33 degrees. And the humidity was somewhere between, I would say, 99 and 100% humidity, depending if there was just a monsoon rain or just not. And then another location where we had been working, and I spent some months there on the drilling platform, drilling into that crater. And another location, so to say a little bit of a contrast, was in the Arctic region of Russia, in the Chukotka area, which was north of the polar circle, where in April we had temperatures of minus 30 degrees Celsius and an ice cover. And so this is a little different to work under such circumstances. So I've been anywhere from polar regions down to all kinds of tropical places. I think I've visited on the order of 50 or 60 impact craters all over the world. So I've seen a lot of them, and it's interesting how different they all are.
In 2010, you were named the director of the Natural History Museum in Vienna, a position you held for 10 years. Can you tell us about that?
How did that happen?
Well, that was interesting because I was a scientist at the University of Vienna, which I still am, a professor. And but one of the things I always did was I always tried to tell the public what we're doing, because I have the philosophy that most of us scientists who work in basic research are paid through taxpayers' money, and the least we can do in giving something back is to tell the public what we do and why we find it interesting and exciting. So I was kind of known among journalists, and I had been participating in some television film projects and so on. So people knew me, and I was kind of contacted by some people from the search committees that they said, hey, there's this position available. Do you know about it? And of course, we don't ask you to apply, but we just wanted to tell you this is available. And so I thought, okay, well, it's interesting. And I didn't plan to apply, but I thought, okay, I'll just throw my hat in the ring. Who knows? And I was utterly surprised when eventually, within a few months, I was chosen as the new Director General of the Natural History Museum. Now, the Natural History Museum of Vienna has a particular attraction for people working on meteorites because it is the oldest meteorite collection in the world. It was founded, the first meteorite that was included in that collection fell in 1751. And that was at a time when people yet did not know where meteorites came from, as we have already talked about earlier. So now that collection has thousands of meteorites, many of them are famous ones, and people have been studying meteorites there for a long time. There were very famous people who worked there. For example, Carl von Schreibers in the 19th century was a director of that natural history collection. And now the mineral schreibersite, which is an iron nickel phosphide, which is found in iron meteorites, is named after him. Actually, he was a zoologist. He had studied zoology and medicine early on, and then found meteorites much more fascinating. So I think it tells you something. And or the Wittmann-Steffen patterns, which tell us about the inner structure of iron meteorites, they were discovered in Vienna in the collection. So that was an exciting place to be, and I thoroughly enjoyed being able to do things for the public, and think we managed to get a lot done there.
You made an impact.
Well, in a way, for example, the meteorite hall itself was relatively outdated when I became director. It hadn't been changed in, 30 years or more, and a lot has been discovered. And one of the things that I found a little disturbing is, so there were all these meteorites in all the cabinets there, but there was no explanation. So it was just the name and the location. And while this is great for the expert, they stand there and look at this forever, the general public, and I observed that, they kind of look left and look right, that they see lots of brown and gray stones, but nothing else, so they walk on. And I wanted to change that. I wanted to convey the fascination of meteorites. And in general, this is kind of was my approach, not just to have all these things lined up here, one after the other, no matter if it's rocks or animals or meteorites, but kind of explain to the public what it is, what is so interesting about it. And so with the meteorites, we added explanations about meteorites basically are our witnesses of the formation of the Earth and the solar system. By analyzing them, we find out which processes went on that formed the Earth, how old the Earth is, and things like that we learned, or also the danger of impact. So we constructed a little animation kind of thing where you can hit Vienna with asteroids of different size, which we call an impact simulator. And so people can see what happens when a crater forms, how much destruction it really causes. Or we put all the Austrian meteorites together to tell people what's there. Or we had meteorites that came from the planet Mars, and they were never really put out there. So we basically learned something about the surface of Mars by studying meteorites. And of course, I put in a corner about impacts and impact craters and kind of tell people why these are fascinating and interesting. And we did that with some other things. So, for example, I managed to put in a new anthropology exhibit. And this is something that the public was very interested in. And there hadn't been an anthropology exhibit in something like over 20 years or so. So when I became director, I said, hey, we need an anthropology exhibit because the origin and evolution of humans going back to Lucy in Africa and the Neanderthals and all these things, that's something that, we get a lot of school classes that come and see the museum. That's something people want to see. And so we put that in new, and that was a big success. We renewed the dinosaur hall. That was also kind of a little dusty, let's say. So we put in one of these moving dinosaurs that, and the kids are standing there, and now they're all frightened, but at the same time fascinated by this moving dinosaur that roars at them. And so my philosophy always was, you want to draw people in, and you want to kind of attract them with something that maybe is a little bit, maybe even splashy, but then you have them there, and then you can teach them something. And you don't do that by just lining up gray rocks one after the other. You don't get people in that way. And it's also, I wanted to get people excited by saying, oh, I didn't know that. That's kind of the thing I wanted to do, and we did that in many things. So, for example, in mineralogy, we put in an exhibit about, there's that famous story about the evolution of minerals. Normally people say evolution, that's something animals do, right? We've heard Darwin, all these things. What, minerals evolved too? Well, in fact, if you think about it, 2 billion years ago, there was basically no oxygen in the Earth atmosphere. So the minerals that formed were totally different from the minerals that form now. So you can call this evolution if you want, in the broadest sense of terms. But this is people stand there and shake their head and say, I didn't know that.
So what differences do you see between what the public knows or wants to know in Austria compared with other countries that you know well, like Italy or the US?
Well, it's I think, I'm not sure yet. There are, of course, differences, but I think there is a global sense that people are fascinated by things in nature. And they want to know. It's something, the inherent nosiness of people, so to say, they want to know something. And you have to get at a level where, as I just said, you get people interested in something. And I give you an example. We had an exhibit, and Guy knows that, of course, because he was there for parts of that, about the origin of the universe. And that exhibit, that special exhibit, had its background is that I was approached by Austrian people from a high energy physics institute that had been working with CERN, this big high energy laboratory, and they wanted to show about the importance of high energy physics. And I said, no way that you can make an exhibit about high energy physics and muons and Higgs and all these other things. People will just glaze over and nobody will come in. However, I said, let's get them with something that is exciting and that everybody wants to know, the origin of the universe. And we start with all the beautiful Hubble Space Telescope pictures, and we have a meteorite, and you have a meteorite there. And the meteorite is 4.5 billion years old. And you tell people, say, this is the oldest damn piece of rock that you'll ever put your fingers on. Now think, when that meteorite formed and the solar system formed, the universe was already over 9 billion years old. How do we know that? Okay, let's continue a little bit. And eventually you get to the Big Bang, and then you have high energy physics. So you draw them in with something, and suddenly they learn a little something about high energy physics. You have an exhibit that shows cosmic rays, that we're permanently permeated by cosmic rays. And this is something that people say, I didn't know that. And so suddenly we are in physics. Nobody would have gone into that exhibit if they said, oh, we're going to teach you about particle physics, But to get them in and interested, I think this is something actually that would be universal. And what I see is the difference, maybe what the percentage of people maybe that go into museums here. I think in Europe, more people go into museums as percentage of the population than say in the US maybe. And the levels are also maybe not quite comparable. So you need to, of course, adapt your strategy a little bit to your local audience. And in America, you have lots of small little museums, local museums, and I think they are very helpful. In Austria, of course, we have some of those too. But to think about it, that at the museum, when I began, we had less than 500,000 visitors a year. When I ended, we had almost 1 million. After 10 years, 1 million visitors a year. Considering that Austria has 8 million people, and more than half of the people coming to our museum were Austrians, we're reaching a fair percentage of our whole population. Now, I think that number doesn't quite scale up in the US, but there are many large museums. And so I think, what we all need to do in all these places is reach out in podcasts and videos and YouTubes and everything these days that we can use and teach people about the fascination that some of us have with the stars, with meteorites, with rocks and so on. And by doing so, I think some of that spark can get out there and tell people that it's not all fake news, that it's not all bad and scientists are in some conspiracy and whatever, but that there is something out there. And when you show them a piece of rock that had come from outer space, and you tell them, how do we know that it actually came from outer space? I think you can reach a lot of people that way. And I think that's universal.
Amen.
That's it for this podcast. I'd like to thank our guests, Christian Koeberl and Brother Guy Consolmagno. I'm Bob Trembley. You can read posts from Brother Guy and me and listen to our other podcasts on the website of the Vatican Observatory.